Good afternoon. I'm from California, University of California, Davis, and in the Department of Biological and Ag Engineering department. So our department, Biological and Agriculture Engineering, celebrating 100 years this year. So it has a long history, legacy, and I want to invite you to visit California and UC Davis and also our department. My topic of my presentation is to extend the food supply chain. It's about the food leftovers. So what you do with the food leftovers, including the leftovers you have on the plate from today's lunch. And when we have leftovers, it's good to have reuse, recycling. However, there are tons of material that are not used, reused, just thrown away. And it becomes a waste. And so this food leftover or waste become waste. Waste management has a large impact on environment, economics, and food safety. And some residual disease organisms could find a way to our plants and to food production. So I will address this topic and about the technologies that can collect and convert these food leftovers or food residuals into energy and fertilizer products. And especially, I will be talking about this solid material, not the wastewater, so it would be the solid material, which are normally destined to landfill or just land applied without the treatment. And so food scraps from restaurants, from homes, and food processing waste that just thrown away. And so there's a large quantities, vast untapped resources. And in the United States, over 34 million tons of food waste is put into landfill. In California alone, it's over 5 million tons each year, and it's thrown in the landfill. So in the landfill, food waste is the largest type of waste going to landfill by weight. And I believe this is very similar to many other countries as well. So we need to develop applied technologies to convert this material into value-added products rather than just throw in the dump. Okay, food waste is highly degradable, normally has high moisture content. It's great for converting into biofuels, biochemicals, and biofertilizers. And if we do that, now we can produce a low-carbon fuel and for renewable energy generation, and certainly reduce the waste going to landfill and reduce the environmental pollution. And certainly we can create industry, emerging new industry, and for job creation, economic development. In California, this exciting period, time of the history, a lot of new policies that encourage, help universities develop technologies or research institutions develop technologies, industry to apply these new technologies for production of renewable energy, especially bioenergy, and reduce the greenhouse gas emissions. California right now has there's a renewable energy portfolio policy requiring the state utilities to provide their 30% of their energy needs to be renewable sources by 2030, and current level is about 20%. So then also there are new legislation coming out requiring a lot of waste to energy conversion projects as well. Those are listed over here. And besides the energy, renewable energy policies and programs, also greenhouse gas emission policies, low carbon fuel, those are listed over here. Since because time limit, I will not be able to go through those. You're very welcome to look them up, and I'll be happy to talk to you afterwards Okay, so the technology, conversion technology, I'm going to spend some time here today, is about nerve digestion. And nerve digestion has been historically used for waste treatment, primarily for wastewater treatment. Most cities have nerve digestion their wastewater treatment to treat the organic wastewater. And so, however, has not been very widely used for solid waste conversion. So that takes a new innovation, application of new technology to make this nerve digestion become mainstream biogas, bioenergy technology, not just the wastewater treatment technology. Nerve digestion is a biological conversion process, use a mix of microorganisms that convert anything biodegradable into biogas, and also have some leftover solids, nutrients, water. And the biogas contains methane mostly, has 50 to 70% of methane, and directly combustible for electricity and heat generation. And the methane can be purified, used for compressed natural gas or liquefied natural gas. And certainly biogas can be used as a feedstock for raw gas for some other chemical transformation. And so for us to take the food, the leftovers, food waste, convert into biogas, later convert into biofertilizer, return to soil, that will help us to close this loop, right? Farm to fork, and to fill, back to farm. So that's the goal. My research one of a major focus of my research has been biogas production and also biofertilizer production from the food waste or in other organic waste. So I have a biogas energy project at UC Davis that I have run for over 10 years. So the goal is to develop advanced nerve digestion technologies and take from lab to commercial scale and commercialize it. So we have taking the high solids nerve digestion technology development in my laboratory as part of this project from laboratory to commercial levels. I wanted to tell you a little bit about the process, but then focusing on two larger commercial projects we just completed in the last 3 years. And so a number of agencies, including U.S. federal and state agencies, funding our project, and as well as private industry partners on this project. Want to acknowledge their support. And high solids nerve digestion technology is the one developed in my laboratory. It's a 3-stage thermophilic digestion system. It can take a variety of organic waste, especially food waste, different types, different amounts, and then we can fast degrade, convert into biogas a really short time. At thermophilic means is around 55 degrees Celsius. Okay, so we can certainly run lower temperature, but because of it's a faster rate, smaller digesters, and also at that temperature, the environment that we create, we're able to destroy the pathogens that can come in with the feedstock, like food waste, so then make the leftover, the residuals for fertilizer production use safer. And so have a high energy output. Okay, so it's about 15 years. We started in the lab and doing all the testing, proof of concept. Later, about 2006 or so, now I built a whole pilot plant at UC Davis to demonstrate, test this technology in a small commercial scale. And after successful completion, and the use, and then we scaled up into commercial level, especially past 5 years. And we have 3 projects in Sacramento, Davis area. We built for waste conversion using this high solids nerve digestion technology. And one of the projects was completed last year. about a year and a half ago on our campus at UC Davis. And it takes all the food waste, some animal waste from our campus, combined with some food processing waste around the Davis area, and to convert into biogas. The biogas got cleaned up and used for electricity generation. The electricity produced is provided to the university grid. Okay, and so you see this is a system here. So you have 3 tanks. So those are 3 digester tanks, and from the right, so that's where the material coming in, and there's a machine that can separate the material that we don't want, like plastics, metals, tin cans. We can separate those. Then the organics grind up and fed into the digester. The material going to the first digester first, get the liquefied, converting into organic acid. We call hydrolysis or the genesis process. Then the material moving to the second digester. That's where most of the digestion biogasification occur. About 80% of biogas produced in the second tank. And so now the residual material going to third tank, finish up is what we call polishing tank. About 20% of biogas is produced there. The first tank in the front here is an effluent storage tank, and where we take the material, make fertilizer products, and that go into the farm. And so the equipment sitting in the front, there are biogas clean up, and we remove moisture and sulfide. Then biogas put into microturbines. We have 4 microturbines, each one is a 200 kilowatt capacity. And so together is 800 kilowatt generation capacity for electricity. But then the waste heat from microturbines is converting to more electricity, another 125 kilowatt, using organic Rankine cycle equipment to convert waste heat into electricity. So the whole facility has 925 kilowatt, almost 1 megawatt generation capacity. So digester system designed to treat about 50 tons per day, and about 25% dry matter in the feedstock. And so you see some numbers already shared with you, and so the size of tank, total 3 digester tanks has a volume of about 450,000 gallons working volume. Okay, just another picture showing the equipment sitting in the front. That's the we call bioseparator that separated the contaminants, grind material, and put into digester. So in the past year or so, about 95% material that was brought in, fed into digester, but 5% rejected, sent it back to the material recycling facility. That's plastic and metals. Types of material coming into the gate, a lot of food waste from restaurants, and also expired food products, and food product cannot sell, have to be destroyed by the food processors. You see ice creams, dairy products, tomato paste in big boxes. So all kinds of material. We have close to 20 types of material coming through the gate, and a different types coming in. And but however, we are able to convert this material into biogas that are rather consistent in the quality for energy generation. And so we have provided great public education. We constantly give tours, and that provides a lot of impact for the public service. The electricity produced from this facility currently is provided to new zero net energy community on campus. It's a district on campus. The university built have housing, student staff housing, and also some classrooms, research institutes, and so it's the largest zero net energy community developed at the university in North America. And so our biogas energy is providing about a third of electricity or energy used by this community. The other 2/3 comes from solar energy. You see the solar panels on the roof and over the parking lot. So that generates the rest of energy. And so this technology has also been used in large digester facility in Sacramento. In the city of Sacramento, it's about 100 tons per day facilities, twice as big as the one on campus. The biogas here is cleaned up and methane purified, used for vehicle fuel. So it has a fuel filling station for trucks, buses coming by. So the methane is used as a compressed natural gas. We call renewable natural gas. And here's the picture of the facility. If you come close or interested in touring such a facility, I'll be more than happy to arrange. You see the digesters sitting on the right side, and their filling station, these trucks are filling methane produced from digesters. And also similarly, food waste, food processing waste, food products that have to be destroyed coming through the gate put into the digesters. And in addition to extract the energy from these waste, we are doing a lot of research, product development to produce solids and liquid fertilizers from digestate, digest effluent. So after energy extraction, all the good nutrients, macronutrients are still remained in the liquid. And so that's where we do a lot of research, product development. We have produced the highly concentrated solids products and also liquid products for the plants. And California is prime land for fruits and vegetable production, and it requires a lot of fertilizer products, so that's why we are creating products for those markets. So we have greenhouse testing, and also we are doing a lot of field testing on the processed tomatoes and orchards. And with that, I will, because of time, I will have to stop here. I want to acknowledge my students and colleagues, and especially the colleagues from industry closely working with us, and a lot of funding coming from both the public-private agencies. Thank you for your attention. I'll be happy to answer questions. Thank you.
Thank you. Any question? Oh, okay.
Thank you. Thank you. Thank you very much for the excellent talk. Just wonder, do you consider the types of leftover, a separation of the desired leftover and/or the mother inoculum as a hurdle in this exercise? That's one. And
Okay.
what is
Can we start with that first one?
First one, okay.
I
Yeah.
kind of
The
here,
leftovers, right?
the leftovers, yeah.
What type of leftover must you get, and how do you separate them, right?
Mm-hmm.
And the mother culture for this particular exercise. Are they
Interesting. Yep.
are they the hurdles in the whole exercise?
Yeah, so these are the food waste that coming through the gate, and we have a machine that takes all the packaged material and break it up, and then separate the plastics, wood, metals from the food waste, the food material, and the food waste ground up and then collected and put into digester. So it is we call separator. Basically, it's a vertical hammer mill that break the packaging and use air to eject the materials through the separation. Does that answer your question on the separation?
Well, I suppose
it's mechanical.
I suppose to that extent is to a certain extent, because we do not know where you actually. I mean, you must have a choice of certain part of waste that will be coming in. Would you?
Yeah, we do have selection. It's
Okay.
primarily source separated food waste and also food products.
Okay.
And but 95% of these material go into digester, only less than 5% is rejected.
Sure.
So that's about separation. You asked about the inoculum, right?
Yeah,
so
the mother inoculum. Would that be
inoculum, digesters have a stable microbial population in the system, not relying on any microbes coming with these products or feedstock to do the job. However, these materials do come with all kinds of microbes coming in. And so they do have some influence on the first stage. That's why we separate it. So first stage reactor is acidic. It's a hydrolytic acidic reactor, pH 4 to 6, about 4 to 5 range, and very acidic, large bacteria there. And but then the second and third stage are mainly methanogenic process. And so then the bacterial microbial population is narrow and for biogas production.
So your output of 690 kilowatts, right, for your 50 liters meant, I just wonder, is that your optimum or is that you can go further?
Okay, so that's a very good point. So the whole facility, 925, I put down 600 kilowatt approximates from this biogas. But that's where from this 50 ton per day facility, the food waste. That's pretty much the level you can get on the food waste. Yeah. Thank you.
Other questions?
Yes.
Yeah, you mentioned about 3 stages of digestion. First stage, did you use the enzymes also in the process, or you were relying on the lower pH and the microbial?
It's totally microbial. We don't have, we don't add any enzymes, right? It's a microbial process, and the bacteria in the first stage are hydrolytic. They have their own enzyme system. These are anaerobic bacteria. They have their own enzyme system to break down the material. We don't need to add additional enzymes. Yeah. Yes.
I wasn't sure how you were cleaning the gas up, and do you clean it up and put the gas into any grid that you may have, or is it all used locally on your campus?
Yeah, for the power generation, electricity generation, we only remove moisture and sulfide, some organic carbon, and in there. For the Sacramento facility, they actually put methane into the cars. In there, we actually also separate the methane from CO2, carbon dioxide, so make the methane purity. The biogas from these facilities contains about 60% methane. So we use membrane separation technology to separate the separate the carbon dioxide from methane, increase methane content over 96%. So that's the separation before going to the natural gas system. Thank you.
Thank you very much.
Thank you. Appreciate it.
Wait.